Okay, I'll get started. What I'm talking about is a topic of spectral zeta functions. And that won't be big enough for people at the backs, I think. So let me enlarge that. This is the abstract. It got truncated on the website because it couldn't handle symbols. So the basic idea is that if you have an operator, A, and you can compute the eigenvalues and they form a discrete set, well, you can define something called the spectral zeta function, which in those cases is just a sum over the eigenvalues raised, or reciprocal of the eigenvalues to the power of s. And this is the number of papers, Berry, Alizade, and Crandall, and both Crandall and Berry I know to be Mathematica users. I don't know about Alizade, but he probably is too. So it's a long-term connection. Now, what struck my interest in looking at this, there's a paper, Belloni and Robinett. So 2009 paper, JPhys A, constraints on Airy function zeros from quantum mechanical sum rules. And I'm not going to go through the paper, obviously, but basically they're solving a differential equation, computing the eigenvalues of this differential equation. It's an Airy function is the solution. They go through some complicated manipulations, and they find that there are certain properties relating these sums of the eigenvalues for this system. So essentially they're solving the Schrodinger equation with a linear potential over a half plane. Now, I'm not going to go through it except to say that it takes them 5 or 6 pages before they go through various mechanics and manipulations, and eventually they produce, late in the paper, a table of identities. And here's this table where they find certain sums. I'm going to define these, but I'm going to show that this is a one-line Mathematica command, so it probably shouldn't have been published as a paper. I think that's the bottom line point I want to make, and I was intrigued when I looked at this to see, what they were doing and why. What I realized was there's something that they didn't know, and I have to admit, as an undergraduate, I didn't know either. But let me just go back into my presentation. I should have closed a few things down, but let's go back into it. So what they were computing was a set of sum rules where A's are the eigenvalues of this operator. So let me just get into the material here. So let's first look at the functions which we're dealing with here. They're Airy functions. Of course, they're built in Mathematica. There's some nice applications of them in DLMF and this book, Valet and Suarez. So if we do a contour plot of the absolute value of the Airy function, we can see it has roots along the negative real axis. That's one type of Airy function. The second type of Airy function is more interesting because it has roots along the negative real axis as well as these two other branches. Or we can do a complex phase plot of 1 over Airy to see the roots of the function quite clearly along the negative real axis here and see the overall structure of the function. So let's do the derivation, and it's absolutely straightforward. If you start with the Schrodinger equation, I always work in dimensionless forms, getting rid of all of the constants. You can always put them back in later, so I don't understand why so many physicists include h-bars and everything when you can get them back in, and it just makes everything more complicated, leaving them in the equations in the first place. But you start with the equation, and you want to apply the boundary conditions. Now, I noticed that D-solve's been enhanced, but you still can't handle directly, as far as I could see anyway, the second of those boundary conditions directly. You have to take a limit or a series expansion to do that. So the first point is, my first thing is, I tend to, I don't know how many people use or are aware of this notation, but within Mathematica there is a map notation for pure functions. And you will see it occasionally when you do a D-solve. You'll see this map notation coming up. And instead of hashes and ampersands, I prefer to use the mathematical notation, which Jason Harrison added in. So we can define the Schrodinger operator as an operator L with a variable x, which is a map between f and negative d by dx, the second derivative of f plus the linear term. This is the potential term. And we can ask Mathematica to solve that. And we get, I realize, and I can't easily scroll here, so let me just, apologies, go 150%. That will be way too small, I realize, of people. But one other feature that I do like is that if you mouse over these, it identifies, I'm using traditional form, but it identifies that this is the Airy AI and the Airy BI function with obviously two undetermined coefficients. If we compute the asymptotic series of this, and I'll enlarge that because it'll be too small again. If we compute the asymptotic series for the Airy function about infinity, we see that it's got a decaying exponential term. But if we do the one for BI, we have a divergent exponential behavior. So we require C2 to be 0. That's one of the boundary conditions applied. And then to apply the other one, we do a Taylor series of the Airy function about 0. And I don't know how many people use this, but you just add an order term to a function. It doesn't work for some types of series, but it certainly works for Taylor series. And we get this first term, our linear term, and so on. But if we're requiring the function to be 0, what we are requiring is that AI of negative e, which is our energy eigenvalue, has to vanish. So what we're interested in is the zeros of the Airy function. And the nice thing for us is that those zeros are built in. So we have the energy eigenvalues. En is the negative an, and an is the standard notation that is used for this thing. So a couple of things we can do. The first of those is we can tell Matt, this may not be best practice, but it's interesting. We just say AI of whenever it sees that pattern is 0. So we're automatically applying those rules. We can just check that that works. So we can also do something that it's not, I don't know if it's still documented, n values. So this is possibly a bad idea, but it still works. Instead of defining an to be a numerical value, you can define the numerical value of an. So I'm just saying the numerical value of an is the numerical value of the built-in thing. And if I want to do this to high precision, I can do this. And I'm also using I'm saving the values when I compute them. So because these, particularly the high precision values, if I want to compute 500 of these, it takes a while. I might as well save and compute them. So once I have, once I've done that, let me just check. Not sure. So I've just executed those. What we then can look at, and again, because I lose scrolling in this mode, what is the numerical value of A1? What is it to 40 decimal places? So, so I can compute and store these zeros. And so now, if we visualize the function, along the real axis, we get the zeros showing up on the function. I'm hiding the code, but this is for, it's just there. It's a simple plot command. So we know where the zeros are. We now know what the eigenfunctions are. But to normalize the eigenfunctions, we have to compute the integral of the function. And we can do that. And and it gets a nice simple result because I've told it that the area of an is 0. It knows about the roots. And now we can define the normalized eigenfunctions. And again, I'm defining the normalized eigenfunctions using the map notation. I think it's nicer. And once we have these two things, we define the normalized eigenfunctions. We now can plot them and just see what they look like. And this is the behavior we see, that here, this line here is our linear potential, the ground state, first excited state, second excited state, and in these units, the energies, which turn out just to be the negative of the roots of the Airy functions. And one thing, of course, that crossing point is the inflection point of the curve, or an inflection point of the curve, which you can see. So we've got the eigenfunctions. Well, now a bit of maths, and this is the maths that Robinett and Belloni were missing, and the maths that they're missing is the Weierstrass factorization theorem, which I have to admit I don't know what the situation is in American universities, but it wasn't taught to me as an undergraduate, and I only encountered it several years later. And we did complex function theory, but we didn't get as far as the Weierstrass factorization theorem. What it is essentially a way of writing analytic functions as products, is one way of thinking about this. So the theorem is stated there. I'm not going to go into the details, and I'm no expert on it. But the key is this result that says if you have a function with simple zeros, you can write it as a product. There are more general cases here, but you can write it as a product which involves the value of the function at 0, a simple exponential factor, and an infinite product. And I think it's clear that this term in the product, whenever z is equal to an, that term in the product vanishes. So this function vanishes at the roots of the whatever function you're trying to do. So it's the generalization of writing a polynomial in terms of the roots of a polynomial is an essential case. Of course, there's convergence conditions, how to handle other cases, and there's generalizations of this, and some very nice ones, but I don't have time to cover those. So just as a very simple example, the Weierstrass product for the 1 over the gamma function, the roots of 1 over the gamma function are the negative integers and 0. And so if you check this, you just get a true, that it's exactly of that form that we have there. So the gamma function's a nice simple example of that. Well, the realization is that the Airy function is also exactly of that form. You can just write it down by hand. It's hard to find that formula, and I couldn't actually, there was one paper I found that actual formula, and I assume there'd be a number of Russian books that have it, but in the Western literature, it's really hard to find that explicitly stated. But it's obvious. I mean, it's just an application of the Weierstrass theorem. So again, as you can see, this bit will vanish at the Airy zeros. Now, however, if you define the partial products of that, just to see what it looks like, and you try and visualize it, that's with 5 terms in the product. This is with 100 terms in that product. Its convergence is rather slow. It works, but it's a slowly convergent thing, but you take the product to infinity and it does converge to the function. So the process that we want to do to work out the sort of sums that are involved is involved in something that is essentially obvious, that if you want to convert a product into a sum, you take the logarithmic derivative of it. And we can take the logarithmic derivative of the Airy function, and it's just that, which is sort of obvious. But we can also compute the logarithmic derivative of the infinite product, and I'm taking just the front terms there, which is nice and simple. And if we take the rest of it, we just get a combination of terms. Now, I've omitted the infinite product symbol here, but there's an implied infinite sum. So I'm just taking a generic term in the product. It's much more efficient to do that as long as you keep track of what's going on. I just need to take an infinite sum over these. And so the conclusion is this, that the logarithmic derivative of the Airy function minus its value at 0 is just equal to this sum, which is essentially, well, I haven't seen other people say it this way, but I believe that's just the Mittag-Leffler decomposition of the function. But this can be expanded in a power series in Z, and if you do so, what the coefficients of that turn out to be these Airy zeta functions. It's just if you do the power series expansion, you can check that, so you get the Airy zeta function, and that turns out to be analytic for as long as the real part of S is greater than 3/2. And so some properties of this have been studied. Okay, moving on. if you define alpha to be this ratio of these two terms, which turns out to be, it can be expressed in closed form in terms of gamma functions, if you do that, you can do the series expansion of both sides of this. So this is the left-hand side. This bit here is the right-hand side. I'm using the fact that alpha is related to these gamma functions, and if I do this, the series is immediate, and you get this, the Airy zeta functions at the integers greater than or equal to 2 are all just simple polynomials in that ratio. Nice and simple and elegant. It's very easy to get that result. So, well, what Belloni and Robinett were looking at these products, and that equations that I showed earlier are essentially this series of results. So this is the difference between two Airy zeros, and you're interested in this infinite sum. And they found these interesting combinations which they were surprised by. But I'll just show you that it's essentially a trivial result, that if you take the pth derivative of the logarithmic derivative of the Airy function and you subtract off one of the terms in the sum, then just by interchanging the differentiation, the summation, you get the pth derivative of z minus a in the denominator. And so their sums, which they are after, are just taking the limit as z approaches one of the roots of this. And what you get is it can be expressed in closed form. And if you look at this, we've basically got the pth derivative of this function evaluated at point. And the bottom line that we get is this, that on the left-hand side we have this logarithmic derivative of the Airy with one of the poles taken out, and it generates all of their sums for them. So my point is that's a one-line command for generating every one of their sums. It's the whole paper that they essentially achieved. So if you, to put that in context, if you do this series expansion, which is one-line command, you can extract all of those SKPs out of it in, well, I lied, it's two lines of code. But essentially that's all of them there. So it's generated directly from the Airy zeta function expansion. Just to be sure that I'm not completely making a mess here, if you do this numerically, or you do it directly, the second power, that's this column here, I've been a bit sloppy where I've put my ends there, the second column there is slowly convergent, but as you go to higher and higher powers, like the fifth power, you get very nice convergence to the result. And I'm taking 500 terms in the sum just to check that it's correct. So it works. My conclusions is, well, sums over roots, undo that. Sums over the roots can be easily computed. The key is the Weierstrass product theorem, which should be well known, but isn't as well known as it should be by physicists, using log derivative to convert products into sums. The key point of this analysis, if you think about it, I did this for the Airy function, but clearly this works for any function that has a product definition. So there's nothing special about this, and all those quantum sum rules applied to one particular function were not required. And they also treat a number of multiple sums, and if you take products of those sorts of results and expand them out, you get all of these more complicated identities, and they just follow again from Taylor series applied to it. So that's all I wanted to say.